Okay, well, thank you very much. So I'm a solid-state chemist, and what I do is I make materials. So today I want to show you how some of these materials that we're making are addressing some issues in sustainability and environment. And in particular, I want to talk about our Materials Institute, which is called PRIME, and how it's trying to address these. So it's this little play on words, PRIME for the future. So what is PRIME? So PRIME is an acronym, so Prairie Research Institute for Materials and Energy. And although it's centered at the University of Winnipeg, there are all sorts of chemists and physicists and material scientists interested in this problem across the Prairie provinces. And also we have recently University of Alberta, so that should be added to that there. But my lab's called the Quantum Materials Lab. We're interested in making new materials, but also as people are helping us make materials and measuring their properties. Okay, so since energy is one of the words in the acronym, I want to talk about energy and useful energy. So that's a big sustainability issue. So how do we use the energy that we acquire from hydroelectric power, from nuclear, or whatever? And this is when we're looking at news stories, science news stories. There's lots of stories about what's going to happen in 2012 or crazy science fiction gadgets. But I'm surprised there's not more news stories on materials and how they're changing the energy landscape, how we use energy in the most efficient way possible. So that's what I want to talk about today. It's one of the issues that we're trying to deal with in my lab through chemistry, better living through chemistry. So how can materials research solve problems related to the environment? Okay, so just a little primer on how we get energy, right? So energy is it generates somewhere, and that's sort of a misnomer, that name. We don't really generate energy. Energy just changes form, right? So in Manitoba, we get a lot of hydroelectric power, right? So where does that come from? Well, it comes from water falling, so we get that gravitational energy and we turn that into electricity, right? So it's just changing form, not generating energy, no matter if it's from nuclear or coal or whatever. We're just changing forms. And we want to do that in the most efficient way possible, and then deliver that energy to our homes and our businesses whenever in the most efficient way possible, right? And so what we're interested in is making the materials that are used to store that energy and how to deliver it and do it in the best possible way. Okay, but there are problems, right? So there's always waste heat in this process, right? So why is that waste heat bad? Well, it leads to thermal pollution, right? So and that's actually a really major issue, especially if you're looking at things on the industrial scale, right? So I like to clarify, sort of what do I mean by waste heat? There's really two different types of waste heat, right? So the first is something we can do about, the second we can't do anything about. The first is what I'm calling technological heat loss. So that's because we haven't designed the hydroelectric plant the way we want it to. We don't have the right materials to put in our wires to get to our homes. We're always losing energy along the way, right? So that's something that we can do about. I like to argue that one of the big impacts we can make is through chemistry. So chemistry can help us solve some of these issues, designing materials that can do these kinds of things. The other one we can't do anything about, so that's entropy, right? So entropy is from the second law of thermodynamics, if you've taken that in chemistry here. But entropy is a very familiar concept. Everyone knows this if you're trying to organize your sock drawer or wondering why you have to clean your house all the time. It's a natural process where the universe goes from an ordered state to a disordered state, right? And that's something we can't get away from. One of the byproducts of that is always waste heat. So no matter what process we actually design, there's always some heat that's lost. So we have to just give up on being 100% efficient. We have to make do with what we can, what changes we can actually do with designing the process itself. So the second law is really important. Actually, Stephen Hawking, the famous physicist, was asked, if aliens were going to come down to the planet Earth and destroy us unless we demonstrated we're intelligent, what would you actually tell them if you give them one sentence? And he would say, I would tell them that we understand the second law of thermodynamics. That's what he would tell them. So it's a really, really important physical principle you see in biology and chemistry and all over science. But what it tells us is that we can only use so much energy as work. There's always some energy that's lost in that process, right? And unless you're at absolute zero, so absolute zero is minus 273 degrees Celsius. I know it's hard to imagine anything colder than Winnipeg winter, but it's much, much colder than Winnipeg winter. Unless you're at absolute zero, no process is 100% efficient, right? So there's always some heat loss. So we have to make do with what energy we have. So that's the second law. If you're interested in what the other laws are, there's no equations in my talk or anything, but just if you're interested in what they are. So the zeroth law is that you must play the game. So that means that you have to follow the laws of thermodynamics. The first law is you can't win at the game. So that just means that all the energy that you have to just change forms. You can't make energy out of nothing, right? So that's the first law. And the second law is you can't even break even, right? So even if you can convert all that energy into the form that you want, some of that's going to be lost, right? Except on a very cold day, except if you're at minus 273 degrees Celsius. And then the third law is you can't get that cold anyways. No one can get to 0 Kelvin, right? So there's always some energy that's actually lost in this process. Okay. So there'll always be thermal pollution, right? So you'll always have waste heat that's delivered, right? And on a large scale, we think about things like global warming that contributes, and that's a really bad problem. On a small scale, things that we can see in our environments, we see that in our lakes and our rivers, where the temperature of water changes function of time. That changes the chemistry, that promotes algae growth, and it changes ecosystems. That's a really bad problem. And some of that we can't do anything about, right? Just the process itself is the second law. But some of that we can do something about. So I want to talk about how we can do something by designing materials which can use energy in the best way possible, and convert it in the best way possible and store it for as long as possible. Okay, so I'd like to argue that the solution of this is through technology, and in particular through new materials. So basically anything that you see that's technological on my Mac and the PC here, when I'm talking to the microphone, everything that I see that's technological has to do with electronics, I like to argue was designed by a solid-state chemist. Someone had to make that material and test its properties. And solid-state physicists probably perfected them, but solid-state chemistry is behind a lot of the electronics that we see today and a lot of our modern technologies. Someone had to actually figure out how to make those materials. And solid-state chemists have, a lot of them have turned towards addressing issues in the environment, since we helped create some of the problems in the environment, you could argue. And we're turning to things like how can we make better batteries? How can we make better rechargeable batteries? We're interested in that in PRIMED as well. How do you make better batteries? How do you make better solar cells that can grab onto as much energy as possible, right? How do you make very high efficient wiring, right? So how do you store energy properly? So solid-state chemists are interested in all sorts of these problems. But if I had to say like there was one project that was sort of like the holy grail of solid-state chemistry, I would say it's making a room temperature superconductor. So there's thousands of chemists that are working on this problem, and it's a very seductive problem. So what is it? Well, all materials have what's called resistance, electrical resistance, right? So if you run your computer for a long period of time, your iPod, your iPad, anything, it heats up, right? So why does it heat up? It heats up because when electrons flow through those wires, they don't do so in a nice way. They're bouncing around off other electrons. They see other ions in there. They're bouncing off the edges of the wire. Every one of those bounces results in heat loss. So that's the reason why we have resistance. And all materials have some sort of resistance at high temperatures. But at low temperatures, in the upper right-hand corner, there is a picture of resistance versus temperature. And some materials are called superconductors. There's a magic transition temperature we're calling TC, where it becomes superconducting, resistance goes to 0. So the way to imagine that is the electrons are flowing in perfect straight lines, right? They're not bouncing off each other anymore, they're bouncing off edges, right? And it's actually the most efficient way of transporting energy. Actually, superconductors are the ultimate in green technology because there's no thermal loss effectively. There's some thermal loss predicted by the second law, but you've minimized that process because electrons are moving in perfect straight lines, right? So imagine what superconductivity would do. If we had one that worked at room temperature, imagine how that would change our world, right? So first of all, your electronics wouldn't overheat, right? So that'd be great. You can run computers for long periods of time and do great calculations and things. So that's just a scientist like me. But in society, it'd be a bigger change in the Silicon Revolution, right? So imagine, for example, in Manitoba we have hydroelectric power, right? We sell it to Minnesota, but we don't sell much to Texas. So why is that true, right? Well, imagine if you had a long wire from Manitoba to Texas, there's resistance, which takes away energy from electrons flowing in there, right? So by the time the electricity gets out the other end, there's nothing left, right? It's lost all its energy along the way, right? So we have to sell power to local communities nearby, but we can't do it, right? So imagine if you had superconducting wire, we'd all be rich in Manitoba. We could sell our power where we want around the world, right? You wouldn't have this problem of resistance. But I think one of the biggest changes that would make is in healthcare, right? So if anyone here has had an MRI machine, you might recognize that device in the bottom left-hand corner. So they put you in that torus donut-shaped magnet. So what is that? It's actually a superconducting magnet. They put your body in a large magnetic field. They look at how the water molecules line up in your body, and that tells you about blood flow or swelling, and it helps making diagnostic decisions. So why are MRIs so expensive? Well, room temperature superconductivity doesn't exist. We have superconductors that work at really low temperature. That graph in the bottom right-hand corner is showing you our progress in the field. And it's showing you that initially they're only a few Kelvin, but in the 80s we had this breakthrough where it went up to around 135 Kelvin. Right now it's still not room temperature. Room temperature is like 298 Kelvin. But it's nice because liquid nitrogen is 77 Kelvin. So you can use liquid nitrogen to make superconductors work. And that's why one of the reasons why MRIs are so expensive. You have to cool them down all the time. If we had room temperature MRIs, we'd have MRIs all over the place. I mean, I'd have them in Africa, we'd have them all across the world where you can't get these cryogens normally, right? So it would really change everything about our society. Unfortunately, that graph, the reason why it's cut off from 1990 or so is that there's no progress. We don't understand how superconductors work. And you can see they're getting more and more complicated in terms of their chemical formulae. The solution to this problem is through chemistry, making new compounds that can actually crack this problem because physicists and air material scientists don't understand how superconductors work, right? So yeah, that's a really huge challenge. And certainly there's a Nobel Prize waiting for you. This was one of the big holy grails of modern science discovering this. But what if you can't win a Nobel, right? So I'm not going to win a Nobel Prize. What's a more practical solution that we can do locally? How can materials change our lives in the next few years, right? Well, I want to talk about certain class of materials that our lab's been working on that can hopefully be used in the near future. So we're working on materials that are called multiferroics, right? So ferrous is the word for iron. Iron is magnetic. Multiferroic is actually magnetic and electrical at the same time, right? So it's a very efficient way to store energy. And we've made about a dozen of these new materials that have a wide range of temperatures you can use them for. And they're great for a way of energy storage and transmission, right? So that's what we're looking at right now. And you don't have to look very far to see how important these materials are. If you just type in multiferroics into Google, you'll see tons of hits, and especially if you type multiferroics in environment. This is a recent story taken from the University of Minnesota where they've actually made one of these multiferroics. And they showed it creates electricity from waste heat. So what's that? So what are they claiming there? Well, they're claiming that usually there's heat that's released in a process that you can't get back. With these multiferroics, you can reabsorb that heat and use that as electricity again, right? So they're very complicated materials, but they're being used in devices. And now we're trying to work with people like Manitoba Hydro to figure out how we can use some of these multiferroics for short-term solutions and possibly longer-term if we develop really efficient ones in the province of Manitoba. So it's a very green source of energy, if you'd like. So with that, there's lots of materials I can talk about, but I think Keane's going to drag me off stage in a little bit. But thank you for your attention, and I'm happy to take questions off the question board later. Thank you.